Very good. Thank you. All right. So if you were at the last webinar, we talked about energy and work, power, and things like that. What we're going to focus on today are FRQs related to those topics. If you guys weren't at our last webinar, you might not have heard us talk about the new format of the exam. The exam will be a 45-minute test. It will be all FRQs. It will not cover the last couple of units. It won't cover any of the electricity stuff. It won't cover waves and sound. Other than that, we don't know much about the format of the test. We don't know the dates. There are going to be 2 dates that you can choose to take the test on. We should know more about the actual format and those dates on April 3rd. And as soon as I get that information, I will pass it along to your teachers. This PowerPoint that I'm using today is a little modified from the one I used last time. So I'll send this out to teachers after the webinar. I'll also send out the link to the recorded version of this. So if you want either one of those, just email your teacher and you'll be able to get to it. First of all, I want you to read through this FRQ. And I want you to attempt, just on a sheet of paper or whatever you have nearby, to answer part A, both part 1 and 2. Just sort of sketch it out, see what you can do with it. So again, read the whole prompt, and then try to sketch out just on a scratch sheet of paper somewhere, part A, sections 1 and 2. Let's take about 3 or 4 minutes to give you to try that. While you're working, 2 things that you want to remember. Number 1, the equation for elastic potential energy, like the energy stored in a spring, is 1/2 kx squared, where k is the spring constant and x is the distance the spring is displaced, compressed in this case. Also remember the equation for kinetic energy. Kinetic energy is 1/2 mass times velocity squared. I'll be quiet and give you just a couple of minutes to work on this, and we'll go from there. All right, so let's take a look. So we're starting off with the block at this position 0, and then we're pushing the block backwards, compressing the spring a distance of -d. And what it wants us to know here, it tells us that after we compress the spring, we're then going to release it. And then once the block gets back to 0, this part of the track after 0 is a little rough, so there's some friction there. Eventually the block stops right here at 3 times d. What we want to do first, though, is what part A asks us to do, and it asks us to sketch the energy, number 1, the kinetic energy of the block, and number 2, the potential energy of the block between -d and positive 3D. So I'm going to go to an axis here so I can sketch this a little bit better. So what we need to think about is that at negative D, all of the energy is stored as elastic potential energy in that spring. I don't know how much potential energy there is. I'm just going to go up to 1, 2, 3. I'm going to go up to 4 units. That's where I'm going to start. So at negative D, all of the energy is potential. And then between negative D and 0, that potential energy is being converted into kinetic energy. We're assuming there's no friction between negative D and 0. So that means that the initial potential energy that I have is going to be equal to the kinetic energy at x equals 0. We're assuming we're not losing any energy in the process. Now, some of you would come in and just put in a straight line like so, and showing me that the potential energy is going down between negative D and 0. That's right. But what's not right about that is it's not a linear relationship. Remember that the potential energy is 1/2 kx squared. So the bigger the x, the bigger the energy. It's not a linear relationship. It's more of a quadratic kind of relationship. So what that means is that the energy conversion from potential to kinetic is going to be really fast at first, and then it's going to level off. So instead of being a straight line, it may look more like a curve, something like that. From there on out, from 0 all the way to 3D, we're going to have no potential energy. So I'm going to label this as the potential energy, like so. That's my potential energy curve. Now, as far as kinetic energy goes, we're going to start off with 0 kinetic energy. And then the further out, and to begin with, the rate of change of potential to kinetic is going to be really, really high, which means the slope of this kinetic energy line that I'm going to draw is going to be really steep at first. But then the closer the spring gets back to that equilibrium position, the 0 position, the rate of conversion is going to slow down. So the slope is going to moderate. What I'm trying to tell you is that we're going to get sort of a concave down curve, maybe something like that. This is going to be the kinetic energy line. Now, from 0 all the way to 3D, what's happening is that kinetic energy is being converted into heat because there's friction. The frictional force is constant, the same at 0 as it is at 3D, which means the conversion from kinetic to heat should be constant. It should be a straight line all the way from 0 to 3D. And it's going to be kind of hard for me to draw on the screen. Let me do the best I can. That should be a straight line like so. So this is my kinetic energy line. This is my potential energy line. Number one, anybody have questions on why the graphs look the way they look? So here's the rubric for that part of the question. Notice for sketching the energy curve with a reasonably correct shape between negative D and 0, you got a point. For sketching two curves from negative D to 0 with shapes and values such that the total energy is constant, meaning that we're always summing up to 4 no matter where we go. That's another point. For sketching potential energy equal to 0 at x equals 0 and at 3D, perfect. And then for sketching that the kinetic energy is linear from 0 to 3D, this part of the graph, you got another point. So 4 possible points. You might not have gotten all of those, but hopefully you got some of them. Now let's move on to the next part. The spring is now compressed twice as much to x equals 2D. So we're pushing the spring in 2 times as far. A student is asked to predict whether the final position of the block will be twice as far as x equals 6D. Because remember, initially, when the spring was compressed a distance of D, eventually the block ended up at 3D after we let it go. Here it says the student reasons that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring. So it will slide further along the track before stopping at position x equals 6d. So I want you to take just maybe 2 minutes, and I want you to try to answer just part B. So take 2 minutes, look at part B, try to answer part 1 and part 2 of part B. So 2 minutes starting now.
Matt, can you show the initial problem at the beginning for those people that are just joining, just so they can see what's going on?
Yeah, sure can. Here we go. All right, so there's that initial prompt. And we'll go back to the part of the question we're working on here in just a second. All right, so let's go ahead and talk about part 1 and 2 here. So first of all, we want to know what aspects of the student's reasoning are correct. Explain why we think that. And then 2, what parts of the student's reasoning are incorrect, and explain why. Make sure when you're answering a question like this that you label your answer as part B, subpart 1. Answer that part. Part B, subpart 2. Answer that. You want to make it as easy as possible for the reader to find your answers. So clearly label them. Answer part A, label it. Answer part B, label it. Answer part C, label it. Answer part D, label it. And if there are any subparts, label those as well. So here's part B, subpart 1. I'm just going to go to the rubric and take a look at that. So for part 1, what we really wanted to talk about is that the block will, once it gets to 0, x equals 0, the block's going to have more energy than it had before, which means it is going to go further. So you might say the block will go further because it has more energy, something like that. That part is correct. That's worth the point. What's not correct is the final position. We're assuming what the student is assuming is if they compress the spring twice as much, the block will end up going twice as far. But what that student is not thinking about is this equation. And that part of that equation right there. So if you compress that spring a distance of 1 versus a distance of 2, this one is going to have 4 times as much energy as this one does, because it's not a linear relationship. It's a power of 2 relationship. So essentially what we want to say in part 2 is that the student's incorrect about the new final position because the spring's energy is not linear. Here they don't really want you to talk about the equation so much. They just want you to say it's not linear. I don't think they would count off if you talked about the equation, but they're looking for qualitative stuff here. If they ask you for qualitative reasoning, they want you to explain it in words. If they ask you for quantitative answers, they want you to explain it in terms of numbers and equations. All right, let's go ahead and look at part C. So here's part C, and there's that word quantitative we talked about a second ago. So numbers and equations, including equations as needed, to develop an expression for the new final position of the block. Express your answers in terms of D, that original distance that we compress the spring. So I'm going to talk about this one in terms of the rubric. I noticed there were 3 possible points on this equation. There's some things you might not be able to get the equation for, so I think it would be just fine for you to put in some words. But let's look at the equations first, and then we'll go back and look at the words. So number 1, they set up an equation for the potential energy, the initial potential energy of the spring when it's compressed a distance of D. That's 1/2 kx squared. Here we substituted D for x because that was our actual distance. This is the equation for the potential energy of the spring when it's compressed twice as far. So for x, we plugged in 2D. And what I hope you see is that when you go through and you square, that the potential energy in position 2 is 4 times what it is in position 1 because of that x squared term. So when you compress the spring twice as far, you get twice as much elastic potential energy. That's all we're saying here. And that's what they're saying in this part of the rubric for indicating that the final energy in the spring is 4 times the original energy in the spring. And they don't word that very well here. We probably ought to say when it's compressed twice as far, it has 4 times as much potential energy. All right, next, notice they set up equations here for work. You got to think about what's happening. Once, so this is our spring, and this is our box. Here's 0. Once this spring gets back to here, remember that friction is acting from 0 on. So friction is doing work. Frictional force is acting in this direction, and it's converting the energy that was in that block, the potential energy that was in this block, into heat. Friction's going to do as much work as there was potential energy at this point. So for a block in position 1, essentially they're setting up an equation, work equals force times distance. The force in this case is the frictional force. And remember that the frictional force is mu times N, mu times the normal force. We're on flat ground, so that normal force is essentially equal to the weight. So that's where mu mg comes from. The coefficient of friction times the normal force. And then times the distance that it slides after the 0 point. So initially, it slid a distance of 3d. In situation number 2, the work is still going to be equal to the frictional force, mu times mg, times some new distance, which we don't know. That's what we're looking for, that new distance. And essentially, notice up here in the written part of the rubric, you get a point for indicating that the frictional force is always the same. The frictional force is mu mg here. It's mu mg here. So you got a point for that, either way. The next big jump for equating that the initial energy in the spring and showing that that's dissipated by friction is proportional to the distance the block slides. So essentially what we're saying here is that the work with the spring in position 1 is equal to the potential energy when the block is in position 1. The work when the block is in position 2 is equal to the initial potential energy of the block in position 2. But remember, that was equal to 4 times what it was in position 1. That's where this comes from. that was also equal to 4 times the work. So you got to do a little creative math here. Remembering that the work in position 2 at 2D is going to be equal to mu mg times delta x2. We're now saying that that's equal to essentially 4 times the work done when the block was in position 1. And that's mu mg times the distance, which was 3D. Now, what I hope you see here is that most things cancel out in this case. Mu mg is the same on both sides. That cancels out. And what we're left with is delta x2 is equal to 4 times 3D, which is 12D. So what that's telling us is that block is going to end up going essentially 4 times further. The initial block went 3D. The block, when it's compressed twice as far, is going to end up going 4 times further, or to a distance of 12D. So if you couldn't work out all these equations, I think if you went in and explained some of that in words, you could get some points. Either way, 3 possible points on part C. Before I go further, questions on part C, because I know some of this math in here is a little confusing. All right, if not, part D, explain how any correct aspects of the student's reasoning identified in part B are expressed in your mathematical relationships in part C. Explain how your relationships in part C correct any incorrect aspects of the student's reasoning in part B. Refer to the relationships you talked about in part C. So essentially, we want to talk about what was right about the student and how the equations fix what wasn't right. So we need to specifically talk about what we said in part B. Now remember, we said in part B that what the student got right is that the block has more energy when it leaves the spring. So essentially, we could use this part of the equation right here and say that the block in position 2 has 4 times the energy that it had in position number 1. And therefore, it's going to go further. Let's look at the rubric. So you could get 1 point here for indicating that the student's correct reasoning that the block has more energy in the second situation is expressed by the calculations that compare the initial energy, which we called mu1, to mu2. So in the second position, the block had 4 times as much energy as it has in the first one. You could word that in a lot of different ways, but you've got to relate it to what you said in part B. Remember, what we said the student got wrong in part C was that the block wasn't just going to go, the student said the block was going to go twice as far in position 2. We know that's not what's going to happen. It's going to go 4 times as far. So let's look at what the rubric here says. For indicating that the student's correct reasoning that the block will slide further is expressed by an equation that indicates that the work done by friction is factor. So this is still talking about the correct parts. The block is going to go further. It's not going to go twice as far. It's going to go 4 times as far. But the reason it's going to go twice as far is because it's going to start off with more energy, and therefore more work can be done on it before it stops. Finally, part D, for indicating that the student's incorrect because the energy scale is not linear. It's based on a power of 2 square. So instead of the spring having twice as much energy, it's going to have 4 times as much energy, and therefore it's going to go 4 times as far. All right, I stumbled on that one a bit, but that's part D. If there aren't any questions, we're going to move on to a completely different question. Here's the second question. I want everybody to take a couple of minutes, read through it, look at the diagram, and go ahead and answer part A. Pay specific attention to justify your answer. Explain why you think your answer is your answer. That's what justify means. So take just a minute, look at the picture, read the prompt, and answer part A, just yes or no, and then give me a justification. Just sketch that out on your sheet of paper. All right, what I'm hoping you're thinking about on this problem is that up here at the top of the path, in both cases, the block has potential energy, gravitational potential energy. And that as it slides down the incline, that potential energy is getting converted to kinetic energy. Now, what we're seeing down at the bottom here of table 1, we're now on the tabletop. So we're going to assume that all of this potential energy has been converted to kinetic energy. In block 2, at this point, that would probably be true. All of the potential energy is kinetic. But now it goes up another incline. So some of that kinetic is getting converted back into potential. What I'm trying to tell you here is in situation 1, table 1, all of the potential energy is now kinetic. In situation 2, most of that initial potential energy is kinetic, but a little bit of it got converted back into potential again, gravitational potential. What that means is that the block from table 1 has more kinetic energy when it leaves the table than it does here. Well, kinetic energy is about velocity. So that's telling you that the block on table 1 is going to leave the table moving faster than the block on table 2. And since they're leaving from the same height, that's really the only thing that determines how far they go. What that means is that the block on table 1 is leaving the table faster, therefore it's going to go further than the block leaving table 2. So do block 1 and 2 land the same distance from the tables? You're going to say no. And let's look at the rubric and look at their justifications. So this was worth 3 points. So number 1, no. Number 2, talking about conservation of energy. So you need to explain that whole bit, that the amount of energy is conserved, that you're starting with potential, and that's getting converted into kinetic. Table 1, it all gets converted into kinetic. Table 2, most of it is kinetic, but a little bit of it gets converted back into potential. But the total amount of energy in the system is constant. You got a point for talking about conversion. You got a point for talking about that the launch velocities are different, that the object on table 1 is going to be leaving the table faster than it is on table 2. Point for that. And then another point for talking about, well, they're going to reach different distances, horizontal distances, because they're leaving the ground at the same height, and therefore it's going to take the same amount of time for them to get there. The only thing that's going to be different are those launch velocities, and therefore the object leaving table 1 is going to go further than the object leaving table 2. Here's a quick, just written out good example answer that would be worth 3 points. Take just a second and read that. So that's sort of a perfect, concise, short answer. And that's really all you need on most of these is something sweet and to the point. You don't need to make up a bunch of stuff and talk in circles. Just get to the point and move on. Let's go ahead and look at the second part of this question. So everybody take just a minute, look at this part, and go ahead and try to answer part B on this part. Just part B. Part B number 1. Let's do that. Just part B, subpart 1. And go ahead and explain your reasoning without manipulating equations. Okay, so let's look at it. So here we have two different setups. Notice that both blocks start at the same height above the table, which means they start with this equal gravitational potential energies. What's different is the slope of the incline. This one says, which block, if either, lands further from its respective table? What you've got to realize here is that in this case, gravity is acting as a conservative force. That it's going to, in this case, all of the potential energy in both situations is going to be converted to kinetic here. And since the initial kinetic energy was equal, that means that I said that backwards. Since the initial potential energy was equal at the top of the plane, that means the kinetic energies are going to be equal at the bottom of the plane. And what that means, since they're going to be leaving with the same kinetic energy, which means they're going to be leaving with the same velocity, they're leaving from the same height, the blocks are going to go the same distance. That's what we're looking for. So let's look at the rubric on that. So again, you're going to say they land the same distance. And what you've got to talk about here is for indicating that the change in potential energy from release to launch is the same in both cases. They started with the same potential energy. At the bottom, they have the same kinetic energy. That means their launch velocities are the same. And since they're leaving from the same height, they're going to go the same distance. So a good 2 or 3 sentences, you ought to be able to answer part 1. Let's go ahead and look at part 2 together. Which block, if either, hits the floor first? Now this part's a little bit more tricky because we already said they're going to go the same distance. But what makes it a bit more tricky is that notice the slopes of these are different. The slope, at least initially here, is much more steep on this one than it is on this one. And what that means is that this one gets up to a higher speed faster than they do in situation number 2. What that's telling is that the average speed on table 1 is going to be a little higher than the average speed on table 2. The block on table 1 is going to get to the bottom of the hill faster than it does here, even though they both end up with the same speed once they get there. This one speeds up sort of all at once near the bottom. This one sped up really fast all the way down. So the answer we're looking for here is block 1's going to get there first because of the initial steepness of the slope. So let's look at the rubric on this one. So again, correct answer is going to be block 1. And we need to talk about that the average speed or average velocity is higher on table 1. It gets to its maximum speed faster. Or we could talk about why the average speed is higher for team 1. It takes a little explaining here. Here's a good example. This is kind of how I would answer it. because the ramp on table 1 is initially steeper. Block 1 has a higher average speed while it's on the ramp, so it launches off the table before block 2. It gets up to a higher speed faster. That's really what they want you to talk about. All right, any questions on FRQ2? All right, we have 2 other questions we want to look at, so I'm going to move on. This one's real short. Everybody take just a minute or 2 and read it and see what you can do as far as a quick answer on this one, FRQ3. This is the whole question. All right, so in trial 1, our block is going to start moving down our incline. In this case, there's no friction between the incline and the box, and there's also no friction between the incline and the table. What you got to think about in that situation in trial 1 is as this box starts moving down this way, since there's no friction between the incline and the table, the incline is going to be moving that way. What I hope that makes you think about is that when the system starts, the block up here has some gravitational potential energy. And as it goes down, that potential energy is converted into kinetic of the box, but also kinetic of the plane. So when the box gets down here, the box has kinetic energy that's less than the initial gravitational potential energy, because some of that kinetic energy is now part of the plane. Or we could say that the kinetic energy of the plane plus the kinetic energy of the box is equal to that initial gravitational potential energy at the top. In the other situation, now the plane is fixed, so the plane can't move. It's stuck here. So what that's telling me is that the box up here has gravitational potential energy. As it slides down, since there's no friction, all of the gravitational potential energy that was here is now kinetic down here. So the initial gravitational potential energy is now equal to the kinetic energy of the box at the bottom of the hill. What I hope that shows you is that in trial 2, this kinetic energy is greater than it was up there, because there's none of that kinetic energy being shared with the plane. So let's look at the rubric. Here's the rubric. So 7 possible points on this simple question. Number 1, talking about energy conversion, that the potential and kinetic energies have to add up to be the same in any situation. For indicating the same amount of potential energies converted to kinetic energy in each trial. Another point for that. For indicating that the kinetic energy is shared between the block and the plane in trial 1. Point for that. For indicating that the block gets all of the kinetic energy in trial 2. Point for that. For a description of the motion of the plane. So you could talk about in trial 1, the plane is going to move backward to the left because the box is moving to the right. And then in trial 2, the plane isn't moving because it's fixed. You could explain why the plane is moving backward if you talked about momentum. in trial 2, we started with the box up here on top. The initial momentum of the system is 0. That means the final momentum of the system also has to be 0. So if the box has momentum going this way, the plane has to have momentum going the other way. So there's lots of different ways you could get to these points, but here's a good concise answer. Take a minute and read through that.
Hey, Mr. Dean.
Yes, sir.
How do we know that the box is moving? I mean, the plane is moving in the first one where it's not fixed?
Okay, since it's not fixed and it tells you that there's no friction between the plane and the table, what that means is as the box is coming down the plane, it's being pushed to the right, which means whatever it's sitting on, in this case, the plane, has to be pushed to the left. And since there's no friction, 0 friction between the plane and the table, if it's getting pushed to the left, it's going to move because there's no friction. Does that make sense?
Yes, sir.
All right. All right, well, let's get to our last question. This is off an exam, I don't know, 3 or 4 years ago. Everybody take just a minute and read the initial part of the prompt, this part up here. And just look at part A to begin with. Part A, part 1. Just part A, part 1. All right, so essentially this is asking us to draw something like a free body diagram, but it's wanting us to show the point where the forces actually act. It's also pointing out that we want to show the forces, not components of those forces. So let's first of all think about what's making the wheel move in the first place. What's making it go down the plane is its weight, at least some component of its weight. So let's first of all draw in the weight. We want to think of the weight as acting on the center of mass of the wheel, which will be right in the center. And we know weight acts straight down. So I would draw something like so. And that's not really straight down. Let me make sure it's straight down. That looks better. And you could label that as weight, or I'm going to label that as force of gravity, like so. Something else that we need to think about, they told us there's friction. Well, the friction's a contact force. It has to happen where the wheel is touching the plane. And remember that friction always acts in the direction opposite of motion. So this wheel is going to be going down the plane, which means friction has to be acting in the other direction. So maybe we want to come to right here where the wheel is touching the plane, and we want to draw friction acting up that plane. And I'm going to label that as F sub F, frictional force. Now, some of you would probably stop there and think you got them all. But the one thing that we're missing is the normal force. We know whenever there's surfaces that are touching, because one surface is pushing down, the other surface is pushing up. And it always pushes up perpendicular to the surface. So that normal force is going to act between the wheel and the plane, because that's where that force happens. And it's going to act perpendicular to the plane. So again, we need to come to where those two surfaces touch and draw in something like that so that that's a 90-degree angle. And we're going to label that as the normal force, like so. My drawing's a little off. It ought to go through the center. You can see it better here with their picture. That looks a lot better than what we had before. But this part was worth 2 points. One for showing the gravitational force and showing that it started at the center and acted straight down. And then another point for showing the frictional force acting opposite direction of motion, and for showing that the normal force is acting at a 90-degree angle perpendicular to the ramp. And notice here it says that should go toward the center. Doesn't have to go exactly through, but should come pretty close. All right, so now let's look at the second part of this equation, or question. Part 2. As the wheel rolls down the ramp, which forces cause the angular velocity of the wheel cause changes in the angular velocity of the wheel with respect to its center of mass? So what you got to think about is change in angular velocity. That means that there's angular acceleration. And what I hope you think about here is that what kinds of things cause changes in angular velocity? What kinds of things cause angular acceleration? And I hope you eventually work your way to the idea that torques cause changes in angular velocity. And if you look at the picture, the force that actually causes a torque is the force that's acting on the outer part of the rim. And it's not acting toward the center. The force that's acting out here on the outer part of the rim, causing this thing to rotate, this is always going to be the case with a wheel like this, is going to be the force that's acting on the rim toward the center, which in this case is the frictional force. Now, you might have gotten through some circular logic. You might have said, well, there's a gravitational force. A component of that pushes down on the plane. Well, the reaction force to that is a normal force. And because there's a normal force, there's a frictional force. You might have talked your way through that. But the easiest answer to this question was just to say the frictional force. And if we look at the explanation of the reasoning here, so again, frictional force, explaining that the friction is the only force that exerts a torque. It's the only force that's not acting on the center of the object, and going from there. So that's 1 point for that part, essentially. You got 1 point for saying frictional force and for saying it's the only force that exerts torque. So now let's look at part B real quick. For this ramp angle, the frictional force of friction exerted on the wheel is less than the maximum possible static friction force. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite to the friction force. Derive an expression for the linear acceleration of the wheel center of mass in terms of m, theta, physical constants as appropriate. That sounds really, really, really confusing. But let's go back and let's go ahead and look at the rubric, and let's just put a picture here, like so. So our plane is theta, and instead of trying to draw the wheel, I'm just going to draw a box. What I want you to think about first is the weight. So there's the weight of our box. That's mg. And I want to break that into components. And I want to break that into one component that's perpendicular to the plane and one that's parallel to the plane. Remembering that when we break a weight component, a weight into its components on an incline like this, that the angle of the incline is going to end up also being this angle right here. We know that this is mg. So what we're really concerned about here, the force that acts opposite of friction, is this parallel component of the weight. And we could find that by saying sine of theta, remember theta is this angle right here, is equal to the opposite side, F parallel, over mg. Which means that F parallel is equal to mg sine theta. Now let's go back and look at what the question is asking us here. So here it's saying that the force of friction exerted on the wheel is less than the maximum possible static friction. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite to the force of friction. This is the force acting opposite of friction. And what we're saying here is that mg sine theta, we're saying that the frictional force, rather, is 40% of that, 0.40 of mg sine theta. We're trying to find the acceleration of the object. So the acceleration, we've got mg sine theta acting down the plane. That's the parallel component of the weight. And then we have the frictional force acting up the plane, and that's 0.4 mg sine theta. What I hope you see is the net force acting on that box down the plane is therefore going to be 1 mg sine theta minus 0.4, which means the net force is going to be equal to 0.6 mg sine theta. Well, what we know is that net force is equal to mass times acceleration. So we could say ma equals 0.6 mg sine theta. Well, mass is on both sides of this equation. So this mass right here and this mass right here cancel out. So we end up with A equal 0.6 sine theta. So that's by far the most confusing part of this problem. But what you had to realize is that what makes the box move is the sum of the parallel component of the weight acting down on the box and the frictional force acting up on the box. Combine those two to get a net force of 0.6 mg sine theta. Set that equal to m times A using Newton's second law, and then solve for A to get A equals 0.6 sine theta. So that was 2 points, a lot for 2 points. What I think though is the most interesting part of this question is part C. So here's part C. In a second experiment on the same ramp, a block of ice, also with mass m, is released from rest at the same instant the wheel is released from rest, from the same height. The block slides down the ramp with negligible friction. Which object, if either, reaches the bottom of the ramp with the greatest speed? Now, some of you might say they're going to get to the bottom at the same time. But remember, there is some friction between the wheel and the plane. That means, let's draw this out for a second. So with the block of ice up here, all of the potential energy up here becomes kinetic energy down here because there's no friction and therefore energy is conserved. With the wheel starts same place. There is some friction, which means the potential energy that we start with is greater than the kinetic energy that we end with. What I'm hoping that shows you is that the ice is going to get to the bottom first. It's going to get there going faster. So the block of ice is going to get there going faster. Now, in terms of forces, briefly explain your answer in terms of forces. Let's look at the rubric on this one. So here we're saying the block. Let's see if I can move this thing out of the way here. The block gets there first. So here it says the wheel experiences a counteracting frictional force. So the block has a greater net force acting on it. The block, the only force acting on it down the plane is the parallel component of the plane. Parallel component of the weight, I should say. So if this is the block, the only force acting on it along that plane is the F parallel. Whereas if we were talking about the wheel, and here's our wheel, we've got the parallel component acting down, but we also have friction acting up. So there's a greater net force acting on the block, and therefore the block is going to have a faster acceleration, and it's going to reach the bottom faster because it's going to have a higher speed. That's what they're wanting you to talk about on part 1. Now, on part 2, see if I can move this out of the way. So briefly explain your answer again, now reasoning in terms of energy. And there's really 2 ways you could talk about the energy. Number 1, you could talk about the block. And what we sort of talked about at the beginning of this is that since there's no friction, all of the potential energy that you start with at the top is kinetic energy at the bottom. But with the wheel, because there's friction in here, some of that initial potential energy becomes thermal energy or heat. Whereas in this situation, all of that potential energy becomes kinetic energy. So the block is going to have more kinetic energy when it gets to the bottom, which means it's going faster. It's going to get there faster. Now, the other interesting thing, and they talk about this on the rubric, another thing that's going on in this case is that the block is just sliding. It has translational motion, linear motion, essentially. So another way to think about this is all of the potential energy of this block gets converted to translational kinetic energy at the bottom. Forget about friction for a second. This wheel is not only sliding down the plane, it's rotating, which means that the potential energy that it starts with is getting converted into, I'm going to say, translational kinetic energy, but it's also getting converted into to rotational kinetic energy. So as far as linear speed, it's going to be going slower because not all of the potential energy is getting converted into linear kinetic energy. Some of it's getting converted in to make the wheel spin. So 2 different ways to answer that question. One essentially saying there's less kinetic energy with the wheel because some of the energy got converted into heat because of friction. And the other is to talk about this, this idea of translational kinetic and rotational kinetic energy. All right, that's our 4 questions for today. Hope that helped. We're going to, let me go back to my first slide for just a second. The next one of these is going to be on the 2nd, April 2nd. It's going to be at 11 o'clock. On that day, we're going to be talking about momentum. And our approach on these webinars from here on out is to do a really brief intro, maybe look at a couple of short multiple choice type questions. But then the second webinar on each topic is going to be just FRQs. So we'll take 3 or 4 FRQs. We'll try to work through them step by step and explain the answers because your test is going to be FRQ. We really need you to be prepared for those. All right, I hope